This second mutations video is going to be showing you examples of types of mutations. And this is what you're going to be doing on your week 3 homework assignment. That last question, step 5, is asking you to illustrate a mutation and then tell me what type of mutation is, how you know the type of mutation, and then the potential impacts that this mutation will have on the organism, okay? So what we're going to do here is we're going to start with a piece of template DNA. That's what temp means up there, template. So that's what the DNA is supposed to be. Okay, that's what this cell, that's what the DNA, the genetic material, is coding for. We need AGC, GTA, CCC, TAC. And I'm sorry I ran out of space there. All right, and so then what we're going to do first is we're going to write out the RNA sequence that would be made at the end of transcription using this piece of RNA. And then we're going to say, okay, during translation, what amino acids should we get? Okay, so you're going to want to have your codon wheel handy. Make sure you know how to use it. And then what we're going to do is say, okay, well, what happens when the DNA gets mutated at this point? So that will be us illustrating the mutation. And then I'll walk you through how we, determine the type of mutation and the consequences. So let's go ahead on your own real quick while I change pen colors. Using that piece of template DNA, go ahead and write out the piece of RNA that will be made after transcription. Now, please note, I did not include directionality in the DNA template, okay? This video is really just trying to talk about mutations, so I didn't put all the nitty-gritty detail on here like you should on your assignment. All right, so for our RNA, it is going to be, remember, there's no thymine in RNA, okay? So A is going to pair with U, G is going to pair with C, C pairs with G, and I'm going to scooch this over a little bit so I'm not as squished at the end. So C, A, U, G, 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 A, U, G. Okay, so then you want to underline your reading frame, so your sets of 3, and I tend to write it that way naturally. Okay, so once you've got that, now I want you on your own to go ahead and look at your codon wheel and go ahead and write out what amino acids you should have. Okay, I'm getting my codon wheel pulled up, so it's right here. Let's see if I cannot block this. Okay, there we go. All right, so you're going to start with U, which is in the top right, and then C and G. So and I have to move this now in order to write on this PowerPoint screen. So UGC, I'm trying to change my ink color here, is going to give us cysteine, CYS. Oh, I read that wrong. I'm sorry. It's not what I just said. Hold on. I'm sorry. Okay, so it's what, UCG. So UCG, I'm sorry, gives us serine, S-E-R. You only have to know the 3 letters. And then CAU is going to give us histidine. That's our second amino acid here. GGG gives us glycine, G-L-Y. And then AUG is going to give us methionine, okay? All right. So that is what the cell needs. Okay, we need a protein that has serine first, histidine second, glycine third, so on and so forth. Okay, but remember, we're talking about mutations. So mutations are going to happen at the DNA level. Okay, so let's go ahead and pretend that the mutation is going to happen. Let's see. Right, where did I put it? Hold on. AGC, GTA, CCC. So I am going to put it at right here. Instead of GTA, okay, we're going to make it GTT. Okay, so that's me illustrating the mutation. I'm showing you where that mutation is happening. Okay, so that's now going to affect my third nucleotide in my piece of RNA, right? So it's supposed to be CAU, but it's not going to be anymore because now the DNA has GTT. So this piece of RNA, so I'm looking right over here, y'all, that it's still going to go CA, but now it's going to be CAA, okay? So now you need to go back to your codon wheel and see what CAA gives us. All right, so CAA is going to give us a different amino acid. That's going to give us glutamine, okay? And so this is the incorrect amino acid. So we just made a missense mutation. So with a missense, I say that it is a mistake, okay? DNA polymerase made a mistake, and that results in the incorrect amino acid being included, okay? So the lasting, and we know that because instead of making histidine, we're incorporating glutamine. Now, histidine and glutamine are two very different amino acids, okay? So incorporating one incorrect amino acid can be detrimental to a cell. And so why this is important is because the cell, in some cases, will die. Okay, the incorrect amino acid shuts down, it makes the incorrect amino acid, incorporating a single incorrect amino acid can cause the entire protein to misfold. And if it's not folded correctly, then it's not the correct shape. If the protein is not the correct shape, it cannot do its job. Okay, and each job is vital. And so sometimes when one job is not done, the entire organism can die. Okay, but it depends on the shape and charge of the amino acids. Some amino acids have a positive charge, some have a negative charge, some are hydrophilic, some are hydrophobic. So if we're just going to play pretend here, pretend histidine is a large positively charged amino acid. And let's pretend that glutamine is also a large positively charged amino acid. Then the impact on the cell may not be so bad because they're both positively charged amino acids. They're probably going to interact with the same negatively charged amino acid when the protein is folding. The shape might be maintained and all might be okay. But what if histidine is a positively charged amino acid, but glutamine is a negatively charged amino acid? Are they going to behave the same way? No. Glutamine will not interact with the normal negatively charged amino acid partner when the protein is folding. So that we know for sure that this protein is not going to fold the way it's supposed to, and it might be inactive. Okay, so the consequence of a missense mutation kind of depends which amino acid is actually incorporated incorrectly. Okay, all right. So now let me go ahead and erase this, and we're going to do a different mutation. All right, so instead of that amino acid, let me get back to my pen here. All right, so instead, we are going to mutate this third nucleotide right here. So I'm going to draw my little line through it. So instead of adding a C here, we're going to pretend that DNA polymerase got confused and added a guanine instead. Okay, so then how is that going to trickle down and mess up our RNA? Well, instead of having UCG, we're going to have UCC. So look at your codon wheel. What is UCC? It's still serine. Okay, and I forgot to erase this other guy. Sorry. Let me go and get rid of this. Okay, so this mutation resulted in us using the exact same amino acid. So this is an example of a silent mutation. because there's no lasting consequence on the cell. Because even though there was a mistake at the DNA level, because some amino acids have multiple codons, we call that redundancy in the genetic code. Okay, you'll look at your codon wheel and go to UC, and then look at that last nucleotide. So UCU gives us serine, UCC gives us serine, UCA gives us serine, UCG gives us serine. So there are multiple codons for the same amino acid. Okay, and so that's again called redundancy. And that's actually a cell's way of protecting itself, because if a mutation like the one I just showed you occurs, there's no lasting consequence because the same amino acid is made or incorporated. Okay, so with a silent mutation, no harm, no foul. The same amino acid, the correct amino acid, gets incorporated into the protein. So no problem there. Okay. All right, so that's a pretty long video. So I'm gonna do the nonsense and the frame shift in the next video.